Hello everybody and welcome to exercise 4 on page 41 of the workbook. In this video we will just be looking at part A of this exercise. And let's read this together. So if beta is an element of S5 has the order of beta squared equals 5, we'd like to prove that the order of beta equals 5. Okay, so this is telling us essentially that we've got an element in our group and we know that the order of the square of that element is 5, we'd like to show that the order of the element itself also has to be 5. Okay, we might start by reminding ourselves what S5 is. That's a set of permutations. Okay, in particular, the set of permutations of the set of positive integers between 1 and 5. Okay, so we're going to write a proof here. So let's start with our assumption, and that is that the order of beta squared is equal to 5. Okay, we know that. Okay, we might start by just recalling what that's saying. If the order of beta squared is equal to 5, it means that if we take beta squared and raise it to the 5th power, we have to get the identity permutation. Now, raising beta squared to the 5th power is going to give us beta to the 10th. Okay, and recall that we can write the identity permutation using the epsilon notation. Okay, so we know then that beta to the 10th is equal to the identity. Okay, but if you think back for a minute to chapter 4, that gives us some information about the order of beta. The order of beta then has to be a divisor of that number 10. Okay, and I'm going to quote the result that we're using there. That's corollary 2 of theorem 4.1 that we're using. Okay, well, what possibilities does that give us? Okay, if the order of beta divides 10, the divisors of 10 are 1, 2, 5, and 10. Those are the only possibilities. So there are 4 possibilities for the order of beta. We essentially need to rule out 1, 2, and 10, okay, because we want to show that the order of beta is 5. Okay, and we can rule out 2 of those numbers almost immediately by noticing this statement that we started with. If the order of beta squared is equal to 5, we know that beta squared cannot be the identity. Okay, because if beta squared were the identity, then we would know that the order of beta squared is 1. Okay, so let's start with that observation. So since beta squared is not the identity permutation, that statement immediately rules out the possibility that the order of beta might be 1 or 2. Okay, that can't happen if beta squared is not equal to the identity. Okay, so we must have either the order of beta equals 5 or the order of beta equals 10. Okay, we'd like to rule out the 10, and then we'll have ourselves a proof. Okay, I'm going to call that equation star. Okay, so to proceed here, let's make use of the fact that whatever beta looks like, we can write it as a product of disjoint cycles. Okay, so we're going to write beta as a product of disjoint cycles. Okay, so it's going to look like beta equals alpha 1 times alpha 2. We don't know how many cycles there are, so let's just assume that there are n of them. Okay, and we also don't know what the lengths of the cycles are, so let's just give the lengths names. So we'll call the length of the ith cycle ki. So ki is the length of the cycle alpha I. Okay, well, if that's a product of disjoint cycles, we know how we would get the order of an element like that. It's just going to be the product, or it's going to be the least common multiple of the cycle lengths. Okay, so we'll make that observation. So since we know that the order of beta is the LCM, okay, of all of those k's, we know from the statement that we made up here that at least one of those k's has to have a divisor of 5. I'm just going to write that and we'll see if we can make sense of that after we have the sentence in front of us here. Okay, so we know star that at least one of the ki's must be a multiple of 5. Okay, I might have said that backwards a minute ago. I meant multiple. Okay, why is that? Okay, well, notice that we've narrowed our order of B down into 2 possibilities. It's either 5 or 10. But regardless of which possibility it is, 5 is a factor of both 5 and 10. Okay, so to get either of those 2 orders, 5 or 10, out of this least common multiple, we know that there's got to be 5 as a factor in one of those k's. That's the only way that we could get 5 or 10 as our least common multiple. Okay, so we know that 5 is a divisor then of at least one of those k's. Okay, let's put that together with something else that we know here. Okay, we also know that beta happens to be a permutation in the set S5, which means that we only have 5 numbers at our disposal to permute here. Okay, so that means you might recognize this logic from a previous problem. The sum of our cycle lengths can't be bigger than 5. Okay, after all, we've only got 5 elements. If those cycle lengths added up to something bigger than 5, then we'd have more than 5 numbers involved here. Okay, so let's think about this then. Okay, we've got this inequality being true, and we know that at least one of the k's on our list over here has to have 5 as a factor. What's the only possibility? Okay, well, if one of these numbers is at least 5, then that means there can only be one number on the left-hand side of the equation. If there were more than one, we'd get a number that's bigger than 5 on the left-hand side. Okay, so here's what we can say then. Okay, the only possibility, therefore, is that n equals 1. That's the saying that there's only one number on our list, and k1 equals 5. Okay, but what is that really saying? That's just saying that we've got n equals 1 cycle and its length has to be 5. So we've just proven that this element beta has to be a 5 cycle. Just a single 5 cycle. And if it's a 5 cycle, we know that its order has to be 5. Okay, and that's what we wanted to prove.